So now Sanjay Mulkarwar ji is an outstanding scientist, and he was in charge of Tarapur, Maharashtra site as a site director. And he is my colleague also. We have worked together for several years. And most importantly, that in addition to Tarapur site, he also deputed to Wano Center, London, headquarters. And from there, he also visited many countries for the several presentations. And recently, he has completed a very crucial assignment in Tarapur, that old pipelines of recircular line of 304L has been replaced with 316LN recently. And both unit 1 has started just after so many years. And unit 2 also be started within 10 days, 15 days. That was a big achievement. So I also request him to cover this. And he has also contributed a lot in the curriculum project. आप शुरू करो.
Good afternoon, everyone. I hope it will be an interesting session after lunch. Thanks, Sinhaji, for giving me a good introduction. I am very happy to inform that the oldest nuclear power plant in the world, Tarapur 1 and 2, is now the oldest nuclear power plant in the world, which is in operating condition. And there were big challenges in starting back these units because of, the old plants. There are very high regulatory requirements for safety is the priority. So starting back that unit on the line, it was very challenging, and it took us nearly 5 years to bring that unit online. And I am confident that Tarapur has given the best operating experience and name to NPCIL. And in future also, it will be operating at its highest capacity and generating revenues for the country. And with this, I start my lecture. My lecture will be very general. It is operational priorities and challenges in operating a nuclear power plant. The topics covered will be, I would like to introduce you to a nuclear power plant, then the operational priorities, reactor reliability and its performance, what are the regulatory compliance requirements, some touch on the radiation protection involved in operating a nuclear power plant, nuclear security and cyber security, which are now essential for a nuclear power plant operation, nuclear waste and fuel management, operational challenges, and solutions and future outlooks. To begin with, I want to just say again what our CMD has said, and again I want to reiterate. Nuclear power is proven power now. It is 24/7 source of clean, reliable, sustainable and cost-effective electricity. It is a very good example for reliable baseload power operation. Nuclear power plants do not emit greenhouse gases or other harmful pollutants, thus helps in global warming, fighting global warming. So merits of nuclear power plants makes it an inevitable option for addressing our nation's long-term energy needs in a sustainable manner. I've just given a figure like if a coal power plant and a comparison of other nuclear power plant, what is the tons of carbon dioxide release? So it is 12 for nuclear reactors, and coal you can say it is 820. So you can see what is the contribution of by operating a nuclear power plant, how this can be brought down very easily. We have to agree that nuclear power plants are complex because of the redundant safety systems requirement and all. Hence, it requires strict operational control. In nuclear power plant, safety and reliability are the topmost priorities. Just to give a brief of nuclear power scenario worldwide, there are around 440 reactors in operations and producing around 390,000 megawatt electricity, and it's 10% of the world's total electricity power production. Just statistics, some may be changing also. US is having 93 reactors and producing around 95,000 megawatt electricity. France is having 56 reactors. China is having 55 operating reactors. India is having 24 operating reactors and it's producing around 8,780 megawatt power. It's around 2% of total electricity production. And our country would like to increase nuclear power share to 10%. Target for the year is around 21,000 megawatt electrical. In order to reduce greenhouse effect worldwide, India is committed to reduce emission levels to 45%, which were at 2005, by 2030. NPCL is the only company which is now producing nuclear power plant, nuclear power in India. It was formed to tell about NPCL. We are many companies in one: quality, design, construction, commissioning, operation, maintenance, waste management, renovation and modernization, upgrades, and plant life extensions. So this all is done by NPCL with some help of DA units also. It was formed on September 1987 as a public sector utility of DA, fully owned by Government of India. It has expertise in multiple reactor technologies: PHWR, BWR, and pressurized water reactor. Assets of NPCL 1,91,607 crore and net worth is 65,475 crore. There are large expansion plans based on indigenous PHWRs and light water reactors with foreign corporations. This is the, if anybody want, this is the NPCL presence all over India. We are having around 24 reactors in operation. 7 reactors are under construction. And reactors at this has been dealt with in detail by Mukesh Singhal ji and all. This is the thing. So nuclear energy, you can see where all the nuclear power plants are located throughout India for NPCL. Next slide. This is the nuclear energy mission roadmap for achieving 1,000 gigawatt by 2047. So present capacity is 8,780 megawatt. Capacity under implementation is 13,100 megawatt. And these are the planned future activity. So ultimately, NPCL plans to contribute half of the capacity of 100 gigawatt by 2047. That is the plan. So now, as a nuclear engineer, we have to go to the basics of what is a nuclear reactor, so that we understand what is the safety requirement and why safety is the utmost requirement for a nuclear power plant. What is a nuclear reactor? A nuclear reactor is a source of heat which is produced by self-contained and controlled chain reaction within the reactor core. Natural uranium is used as fuel in pressurized water reactors and enriched uranium is used in boiling water reactors and PWRs. The most important essential components of a reactors are reactor vessel, fuel, moderator, coolant, control rods, and neutron monitors, etc. To tell you, as a nuclear engineer, we should first understand what is nuclear fission. So we understand what are the products of the nuclear fission and how to control it. You understand, a uranium-235, when it is fissioned by a thermal neutron, it splits. It splits and it gives radiation also, and 200 million unit of MeV of heat power. And the fission fragments which are formed, they are the radioactive which are going to contribute to the radiation to the problem to the nuclear power plants. Now, how a nuclear reactor works? When a slow neutron strikes the atom of uranium-235, a fission takes place by breaking it into 2 or more fragments. During this process, enormous heat energy is generated along with production of 2 to 3 fast-moving neutrons. These fast-moving neutrons are slowed down by a moderator in PHWR and light water in PWRs. The slower thermal neutrons are again used for sustained fission chain reaction. The heat produced in the reactor is used to generate light water stream at high pressure that drives the turbo generator to produce electrical energy. These are the schematics of which are the power plants in use. Boiling water, you can see the reactor vessel. It itself is the boiler where the control rods are there. The back at pointer. Pointer. Pointer नहीं है ठीक ये वाला ठीक है. So you are able to see the control rods inside the reactor vessel which are giving the heat. It directly goes to the turbine in BWR and the water goes to the condenser, gets cooled and electricity is generated. Next. Pressurized heavy water, the reactor is horizontal. You can see the fuel channels, control rods, the steam generator. There is a separate calandria for moderator and its heat exchanger. Then in the secondary, in the steam generator, there is a second loop where the steam is formed and it goes to the turbine generator. Next. This is a pressurized water reactor, Kudankulam power plant, which are operating in India. These are the vessel is, reactor vessel is there, the fuel is there, control rods, then the pressurizer is there to maintain the pressure, steam generators, and again the secondary steam is formed, secondary loop is formed. The water boils in the steam generator, goes to the turbine. Water comes to the condenser which is cooled by seawater and it comes back to the steam generator. So now we go to what are the good features of a heavy water reactor and pressurized water reactor. In heavy water reactor, the good features are we are using natural uranium. The fuel assembly is very simple. The uranium usage is very good. In heavy water reactor, on-power refueling is possible, is done. The neutron dynamics is very good. In accidents, fuel is always below melting temperature. This is the good features of a heavy water reactor. The good features of pressurized water reactors are its simple fueling because it is done offline. The fuel burn-ups, you can go for a higher fuel burn-ups. Simple heat transport system, small number of water systems, and large in-service reactor population. Next. But when the good features come, the bad features also are there. So in heavy water, what we can say the bad features are, you have to use heavy water, which is expensive. The tritium is the issue, it must be controlled. The pipings are complicated. It's having two coolant system and the positive coolant void reactivity. These are the bad features of a heavy water reactor. And for a pressurized water reactor, fuel is expensive. Then because offline refueling is there, the reactor, you have to keep a very high amount of excess reactivity in the core. The pressure vessels are very big power coefficients to control power. Fast operation is needed when you have to shut down the reactor. The short neutron life and fuel melting in accidents is possible in case of PWR. So we just talk about the heat transport system. The PHWR and PWR both are pressurized water reactors. It uses a closed primary circulant to transport heat to the steam generator. In boiling water reactor, the water directly boils in the reactor and same is transported to turbine. Next. So I will in brief just go tell the difference between so that we understand the systems also and what are the difference between PHWR, BWR and pressurized water reactor. The reactor type, the PHWR is horizontal reactor, heavy water as coolant and moderator. Boiling water, the reactor is vertical, the moderator is light water and coolant is also light water. In pressurized water reactor also, the reactor is vertical and both moderator and coolant are light water. The type of fuel used, PHWR uses natural uranium oxide. BWR, uranium oxide, the enrichment is 2.1%. For PWR, it is uranium oxide, it is 3.8% and now it is further improved. Power in PHWR now, there are different type of reactor, 220, 540, 700 megawatt electrical. Boiling water reactor, we are only having 2 boiling water reactors. It was, the initial design capacity was 210, but as the steam generator in the secondary circuit were having leak, it was deviated to 160. And PWR is 1000 megawatt electrical. The thermal efficiency for PHWR is around 28%. Boiling water reactor, it is 30%, and pressurized water reactor, the thermal efficiency is around 33%. Void coefficient is very important for nuclear industry. In the PST, it is positive, moderator, it is negative. Boiling water reactor, coolant loss leads to loss in moderation, negative. Same in PWR also. The type of steam generators, PHWR, they are vertical. Boiling water reactor, the steam reactor itself is the steam generator. And pressurized water reactor, they are horizontal steam generators. Coolant channels, in 220 we are having 306 channels. And in 540 and 700 we are having 392 channels. Boiling water reactor, there are 285 assemblies. And pressurized water reactor, there are no channels. It is a fuel assembly. The most important thing for a nuclear power plant are containment. So PHWR are having double containment. It is having V1 and V2. This area are separated depending on enthalpy. And they are getting communicated to separation pool. Pressurized BWR having a single containment. Pressurized water reactor having double containment with SS liner plus containment spray. Hydrogen separation, they are recombiners. One more important thing for designing a nuclear power plant is how the spent fuel is going to be stored. In PSWR, it is at present stored outside containment. In boiling water reactor, it is stored in secondary containment. In PWR, it is stored in primary containment. This becomes important because in Fukushima and all, you know, there was the explosion in spent fuel also. So in case of any such type of accident where the fuel will be contained, so that's why where the location of spent fuel is there, that also becomes important from that point of view. Next we'll go. Safety system in PHWR, there are no train concept, equipment redundancy, de-rangers to actuate, crash cool down and fire water injection. But now the reactor in PWR, we are having 4 independent train concepts and system energized to actuate, a steam generator, then emergency core cooling system. In PHWR, we are having high pressure passive system, low pressure passive system and low pressure active system. Pressurized water reactor, we are having high pressure injection, active and passive, and low pressure active and passive. Again, one more thing is important from a nuclear power plant is how the refilling is done. Refilling means you have to replace the fuel with a fresh fuel as they get depleted. In PSWR, they are done online. Boiling water reactor, you have to open the reactor vessel, then get access to the fuel pool, and around 1/3 of the batch is replaced. Same thing with pressurized water reactor also. It is offline. 1/3 of the batches is replaced at one time. Operating cycle, PHWR, we have shown that it can go more than 900 days. For boiling water reactors and pressurized water reactor, now we are operating it for an 18-month cycle for both KK, NPP and thermal. So capacity factor for PHWR, we can achieve very high capacity factor because the online refilling is possible. And because boiling water reactor and pressurized water reactor for after 18 months, you have to take an outage for around 1 month time. So for that particular time, the capacity factor will be low. Replacement of failed fuel, is it possible? In PSWR, it is possible to replace the fuel if you detect it. But BWR and pressurized water reactor, it is not possible to replace the fuel online. Fuel utilization is best in PSWR. Discharge, so how much burn up you can achieve is pressurized water you can achieve up to 7,000 megawatt per short ton. BWR is 21,000 and PWR you can go up to 43,000. The excess reactivity in PSWR is very less, so it is very good from the accident point of view and from economy point also because you are not have to put extra fuel in the core. Both in excess reactivity in PWR and BWR is very high. Poison out time because of xenon, this is also one important phenomena from nuclear power plant that after a chain reaction stops, the xenon builds up. It's a poison which you insert the control rods or insert the boron to shut down the reaction. But after that, because of the fission products, xenon builds up. Then you should have a system which can overcome this xenon so that you can start the unit very fast. So, but in PSWR, the poison out time is 24 to 36 hours. But in BWR and PWR, because you are having a very excess reactivity, you can overcome this xenon poisoning. Is the pressure boundary manipulated? Yes. In PSWR, it is manipulated because you are doing online refilling. You are getting communicated with a PST system continuously. In boiling water and pressurized water reactor, when the reactor is operating, you are not manipulating the pressure boundary. Fuel handling system, because it is online refilling, the PSWR filling system is very complicated and it needs regular maintenance. Boiling water reactor, it is simple but requires skilled manpower as it is done manually. In PWR, it is automated. Unlike fuel detection, we have already discussed, it is possible in PSWR. BWR, only you can understand is the gross detection. And in PWR, you can identify the zone in which the fuel is detected. Next. So now, we'll discuss about operational priorities. The plants are designed to withstand all natural disasters like earthquake, tsunami, windstorm, cyclone, floods, lightning and thunderstorm, etc. Plants are designed, constructed and operated based on the codes and standards of ERB. Main aim of the ERB is to regulate the use of atomic energy for peaceful purpose while taking complete care of employees and general public residing in the vicinity of the plant. Plants are operated by highly qualified engineers, supervisors and technicians, and standard operating procedures are used for all the activities. So they are the safety in nuclear Indian NPPs. NPP accord the utmost importance to nuclear, radiological, industrial, fire and environmental safety, overriding the demands of production. Protection of workers, public and environment is the highest priority for a nuclear power plant. There are redundancy and diversity for fail-safe operation. There are independent diverse shutdown systems. There are emergency core cooling system if a normal cool system stops. We are having double containment. All the buildings have to be seismically qualified and the structures have also to be seismically qualified. There are multi-tier safety reviews for maintaining safety in the nuclear power plants. Robust regulatory mechanism is in place to ensure that the reactors are in safe conditions. And the most important thing for operating a nuclear power plant in safe condition is continuous safety trainings and drills. This is also one of the important things. NPP at NPCL are having a very good impeccable safety records. So you can see the average dose consumption by adults staying at the exclusion boundary of a nuclear power plant. It is very less as compared to the natural background. These are the data for the 2024. Means natural background gives you this microsievert per year, and because of a nuclear sites, what are the radiation fields contributing to it? Next. So, and we are having a very good safety record. No incident of release of radioactivity beyond stipulated limits in public domain in over 55 years. We are around 645 years of reactor operations, and we say that we have not released any activity in the public domain. We have already seen this again, but we can go the safety barriers. Safety barriers are available which would, in principle, never be jeopardized. These barriers provide for the confinement of radioactive material. The first barrier is the fuel matrix itself, which will contain the fission fragments. The second barrier is the fuel cladding. The third barrier is the primary heat transport system. Fourth barrier is the primary containment, which is maintained. And the fifth barrier is secondary containment. And sixth barrier is the exclusive zone. But in case of any event, now we have to plan for beyond design basis accident also. So there are emergency planning zones. So offsite emergency zone distance around the nuclear plants are identified in the preparedness stage to ensure effectively implementation of protective measures in case of emergency situations. So these are also identified based upon the plant design conditions and accidents conditions. So we say first is the precautionary action zone, which is around 2.8 kilometers, PHZ we say. Then urgent protective action planning zone. So these zones are where the state authorities and government authorities have to act. They have to be told that what is the population in your PHZ, UPZ, extended planning zone, and indices and commodity planning zone. So this comes into picture when you are discussing about offsite emergencies and how to address the public issues in case of offsite emergencies. So in a nuclear power plant, the emergency classification is ascending order of severity as follows. Emergency alert is, there can be a personal contaminations or a small event. It is called, it is confined to plant, then it is plant boundary, then it is alert. If it goes further, then it is called a plant emergency, where the radiation at the plant boundary can be limited to the permissible limits. But if the event is such that the radiation level are going to increase beyond the plant boundaries also, then it is called a site emergency. So you have to make plan for site emergency also. And if it is hypothetically postulated that the radiations are going to go beyond the site emergency also, site boundaries also, then you have to plan the site emergencies where the district administrators also come into picture. Next. These are the protective action required during offsite emergency. Early phase, when the offsite emergencies are there, then maybe by control access, staying inside the building or shelter itself will prevent any harm to the public. Then if the further radiation dose is expected, then we administer thyroid for blocking. And the further actions are food restriction and control. And if in extreme condition, if required, evacuation may be required. And these are the intermediate phase, when the radiation plume or anything has passed. So what intermediate phase may be required is temporary relocation of public, decontamination of some areas, and long-term food restriction. These are the. This is just we have done the accident analysis of taps 1 and 2 for all the power plant. These things are available. That what is the probability of core damage frequency, even if all the safety systems are in place, is there any possibility of core damage to occur? And for 1 and 2, it is 3.2 into minus 10 to the power minus 6 for reactor year. For 3 and 4 plant, it is 6.5 into 10 to the power minus. And so They are very, very low probability events, but even after core damage, radioactivity will be contained within the contaminant with adequate provisions. For worst case accident scenario, reactor containment pressure can reach design pressure within by maximum 38 hours, and for 1 and 2 it takes around 60 hours. So there is sufficient time for operator to take action and depressurize the containment and prevent the accident. So there is sufficient time available for implementing the required protective actions in the public domain. Now we'll discuss about reactor reliability and performance. How we can say a nuclear power plant is performing in a good way, or the safety are being maintained. So performance, WANO has also, in NPCL also, but WANO also there are performance indicators which tells you that how a nuclear power plant is performing. Are there any fuel failure? How they are maintaining the safety standards? Is there any dose to their workers? How the dose is being controlled? So performance indicators have been adopted to provide quantitative indication of plant performance in the area of nuclear plant safety, reliability, plant efficiency, and personal safety. And when the WANO team visits, or when we tell to IAEA and all, in the nuclear power plant, in the operating plant, these are the main things we discuss about to tell how a nuclear power plant, and when we want to say my plant is operating the best way, we have to, these are the things we have to inform that what are the capacity, what are the factors we have achieved. There are some of the things which, if you are coming to the nuclear industry and all, you will come across these factors like unit capability factors. This is like how much you are able to, what is your capacity and what you are able to deliver. So there are various factors associated with it. Then unplanned capability loss factor, force loss rate, then grid-related loss factor means maybe the power plant are operating in a safe manner, but because of the grid behavior, grid is asking you to bring down the power, you are not able to operate the plant at the full power, or there is a disturbance in the grid which has caused the unit to shut down and all. This all things has been taken care in the grid-related loss factor. Then this is most important, unplanned automatic scrams per 7,000 reactor hours critical. Means when the reactor is critical, in the preceding 7,000 hours, how many times the reactor has been shut down or scram has taken place. This will tell you how your plant is operating. Then unplanned, this is unplanned scram per 7,000 hours. First is unplanned automatic scrams, and the second is unplanned scrams. Means the systems or some of the things are going out of your control, and you have to manually scram the unit. That will come under unplanned scrams. Then one more important thing is safety system performance. There are many safety systems, and you have to ensure that all the safety systems, when demanded, are available for the plant operation. So when you are taking the outage, whether you are able to complete that in defined time and all. So the safety system performance, how many safety systems are there, how many trains are there, how you are going to do the maintenance and all. So safety system performance will monitor your safety system availability and how you are keeping the safety system. So for NPP, these are very good indicators. One more thing is fuel reliability. If your fuels are failing, then it is going to affect the completely the nuclear power plants. So these are the most important thing, that fuel reliability. If there is any breach of fuel, I mean, if it is perforation is there, then there is a chances of contamination to whole plant, and the radiation dose and after effects of cleaning are also very high. So maintaining fuel reliability and good fuel, that is a very basic requirement for, means whichever plants are able to maintain the fuel integrity in the best conditions, so their fuel reliability index will be very high. Then chemistry performance, you know, the nuclear vessels and all are made of SS and all. So you have to maintain a very good reactor water chemistry so that your plant can operate for a long duration, long years. So in the planning itself and when you are operating the plant, you have to ensure that the conductivity, pH, and all the other things are in very good condition, so that even after, like we can say, even our Tarapur plant BWR, even after 40 years, we are able to get a permission to operate it for further, because in nuclear power plant, this chemistry performance are maintained in such a good condition that even after 40 or 50 years of operation, when we take the sample of coupons or see the plant conditions and all, we see it in a very good conditions, and that gives confidence to regulator and all to extend the life. So these are one of the things for plant life extensions and all, which are most important. Then collective radiation exposure. This is also example as how you are operating the plant. If your fuel failures are there, if you're not, your cleanup systems are not in very good shapes and all, so collective radiation exposure of the plant will increase, and it will give an impression that you are not operating the nuclear power plant in a very good state. Then nowadays, the plant is also looked from the industrial accident point of view also. We are not only bothered about nuclear safety, but industrial safety is also given the utmost importance. So industrial accident rates are also calculated, whether small means reportable events are there. So that also are now coming under monitoring. And this is industrial accident rate for the workers also, and now the new terms also for, it has come for contractual workers also who are employed in the nuclear power plants. How much any accidents have taken place to them all, that also. And what I want to say is, in most of the cases, NPCL was comparable or better than world median. But some of the area which we have tried to improve is fuel failure and chemistry performance, where some of the areas where and number of scrams. And in the last 10 years, we have put a lot of emphasis on these areas, and there are many, all the brainstormings and all, how to improve this area, and we have really improved on this performance in the last 5 years. So now we'll talk about the regulatory compliance required. We have to abide by strict national and international regulations, ERB, IE and all. There are regular inspections and audits. So ERB teams and other teams will be visiting the corporate teams and all. They will be regularly visiting the nuclear power site. They will be continuously carrying out audits and all. And they will keep you on the toes for maintaining the safety standards. Then regulatory means, other thing is benchmarking with WANO. So WANO is acronym for World Association of Nuclear Operators. This was an organization formed after Chernobyl event, and it is felt that in a nuclear power plant operation, if any one nuclear power plant operators are like a chain, and it is felt that even if one link of a chain is loose or bad, then the whole chain will be of no use. So to ensure that all the power plants operate in good condition and to share their experience and all, WANO was formed, and they are doing frequent visits. They are having programs on many areas, like peer reviews. They will be visiting your plants. They will be comparing it with their plants, good operating practices. Then they will be comparing the performance indicators and all, what are the events have taken place. And then they will be giving you technical support missions. If they find out that you have having some weakness in some areas and all, they will give you some guidelines how to improve you, in what area you are management or operator area, training area, or if your reportings are not good. So as a friendly way, they will try to tell you that you better look into this matter in a different perspective. Then for each and every activity for a nuclear power plant, documentation and operational transfer is the most important things. For each and everything, we are having documentation. For operating a plant, we are having standard operating procedures. If you are going into, if any alarms comes, then there is a alarm procedure. Then if a situation changes, if it is emergency condition comes, then there are emergency actuation procedures. And it is expected that all the operators, they have to take action on base of their operating procedures, not by their wills. They have to follow the operation procedures, and we have to ensure that the operating procedure and documentation are in such a good manner that if an operator follows that documentation, there will be no human errors and he can bring the plant into safe condition very fast. One more important thing, if you will be a part of a nuclear power plant, you will every time see this word, technical specification and station policy. This you can say for a nuclear power plant is a Gita or Bible. So for a nuclear power plant, every nuclear power plant is having its own approved technical specification and station policy. These are approved by regulators and they are the guide to operate the plant. I will just touch upon what are the important things. Hajila ji has discussed many things like they, as the designer and all, they bring out what are the design parameters and all in which the plant should be operated. So the most important thing of technical specifications are safety limits. You will be mentioned in the documentation. This will be mentioned. What are the safety limits for operating that particular nuclear power plants? Safety limits are limits on process variables within which the operation of the nuclear power plant has been shown to be safe. It has been demonstrated by the designer that if you operate within this parameters, the reactor and the fuel will not fail at any conditions. Safety limits are based on the best conservative design estimates. Then comes limiting safety system setting. So LSS are the instrument set points for actuation of appropriate automatic protection device. So based on the safety system, considering the conservative, then the instrumentations and all, you provide, like if a reactor pressure is exceeding some boundary, which is, so for, like for a pressure vessel is designed for this much pressure, you will give us safety margin and put the safety limit slightly below it. And the limiting safety system, they will be actuating some devices which will ensure that the reactor pressure boundary doesn't exceed the safety limits in any conditions. Then there are limiting conditions for operation. So they are established to provide acceptable margin between the normal operating parameter and the established LCO conditions. Many times, like what I'm telling, there are many safety systems and redundant safety systems for plant operation. So the best thing will be all the safety systems are available to the operator all the time to make the plant in operation. But for maintaining the safety system in a very good condition, you have to do periodic maintenance and testing and all. So this LCO conditions will give you margin that how much time you can take a safety system out of service for maintenance purpose and all. How many protection systems you can, protection channels you can take out of at some particular time and all. So they are also putting a restriction. It is not that, okay, I am having 4 trains of safety system, I will take 1 train of system out for 1 year and do any maintenance and all. That is not possible. That's all limits and all are established by regulator very clearly. And if you are violating any technical specification and all, for starting back the unit, you have to go to the regulator, you have to give all the root cause analysis, justification, and it is not possible that safety violation, you will be doing safety violation. But if you are even crossing the LCO, limiting condition of operation also, that are also, you have to do the root cause analysis, you have to find out the what caused for breaching these barriers, and you have to formulate plans so that in future these LCOs are not met, and then only you will be able to start back the plant after proper review by the regulators. Then there is one chapter for radiological safety in which they will be mentioning how much amount of dose is there, how the areas are classified radiation-wise and all. And it will deal with the instrumentations and measures for controlling the radiation protection. And the last requirement means one of the requirement is surveillance requirement. What is the frequency of testing each and every equipment, relief wall, that setting and all, how much, and in that in-service inspection is also in part of it. Now we'll just, for operating a nuclear power plant, one of the most important thing is, because radiation is also involved, is associated with nuclear power plant. So we'll just touch on the radiation protection. The primary aim of radiation protection is to provide an appropriate standard of protection for man without unduly limiting the beneficial practices giving rise to radiation exposure. We are establishing nuclear power plant, or we are doing any medical services and all, where we want to get some tangible benefit. So that's why we are we are getting exposed to radiation protection. So the radiation protections, the aim is that you should not put a unduly limit on radiation protection if it is giving you a beneficial things. For radiation protection, for a NPP, it is based on Radiation Protection Rule, under Atomic Energy Act 1962, ERB codes and guidelines. Any activity should have net positive benefit. Whatever you are doing, you are setting a nuclear power plant or anything, the first thing is, whatever you are doing, it should give a net positive benefit. Then optimization of protection, or we can say ALARA, as low as reasonably achievable. So that is one of the, and dose limit to individuals. So every contact worker, for quarterly, monthly, yearly, everywhere the dose limit, and the public also. And in case of emergency, how much a radiation plant operator can be given a dose limit, they are all mentioned in these chapters. Effective implementation of radiation protection program shall be ensured by workplace monitoring, personal monitoring, process monitoring, then effluent monitoring, environmental monitoring, shielding and access control. This is just from natural radiation, you are getting 80% of the radiation exposed through natural process, and man-made is only 13%. I wanted to show you a slide like Ajala ji also just mentioned. It is just a practical example of when you see if you compare a dose with the Eiffel Tower. So light threatening dose is the top of the Eiffel Tower. And if you come occupational work, it is equivalent to a height of a man, if you see the proportion. And for a public domain, at the plant boundary where public are staying, it is equivalent to a height of a brick. So this is just to at what level we are giving exposure to public or occupational workers. Just gives a pictorial view. For the radiation effluent treatment in PHWR, we are using evaporators, and zoning in PHWR we are doing based on contamination level. What is the contamination in the area? On that basis, zoning is done. And in pressurized water reactor, it is done based on radiation field. Next. So these are the just in PHWR you are having internal contamination possible due to tritium dose, but internal contamination in BWR and PHWR is not there. Contamination in turbine building is possible in boiling water reactor, but in secondary systems, means PHWRs, which are having 2 cycles, secondary cycle contamination is not possible. Next. We'll skip this. These are the things, instrumentation for radiation protections and all. Next. Next. This is contamination control. Whenever you have to pass a nuclear power plant, you have to do whole body checking. So anytime any nuclear power plant visit and all, you will be seeing this frisking and all, where you have to check whole body contamination checks. These are the respiratory equipments if you have to go to airborne activity area. This is a type of clothing being used in nuclear power plants operation. Next. 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 So now I will go in nuclear security and cyber security. Nuclear security is provided by physical security systems. Armed security forces, CSF is deployed at NPP sites. Protection against the work is protection against sabotage. And cyber security for digital control systems is now must. Nuclear waste and fuel management is also most important thing for operating a power plant. So spent fuel is there for storage, dry cask for storage of the fuel, long-term disposal challenge of nuclear fuel, and safe transporter of nuclear material. So these are the challenges which are expected, which we are expecting a nuclear power plant. Nuclear power plant are having redundant and diverse system for fail-safe operation. So for maintaining them in poised state, online check, functional check tests need to be carried out periodically. While carrying out such tests, probability of human error increases. This can be overcome by excellent procedure, good training, peer review checks, and pre-job briefing. There are limiting conditions for operation. Equipments under maintenance, repair, preventive maintenance have to be brought back in fixed time frame. So all the things have to be planned in a very precise manner so that you are not doing any. So these are the challenges while operating a plant. Decontamination of equipment prior to work. If it has gone through radiation, you have to decontaminate the equipment before start of the work. And there are few equipment which cannot be brought to workshop due to contamination. This have to be repaired in the field itself. So you have to have a very good maintenance team also in the field and all. So the time duration, if the equipment can be brought outside the workshop and all, there are many machines and all by which you can do the good maintenance and all. But because of contamination, sometimes you have to. So these are the challenges which come to operate a nuclear power plant. Few of the plant areas are inaccessible during plant operation due to radiation or airborne activity. If you find any degradation in these areas, you have to go for plant shutdown. So many of times the units are shut down because of such reason. There are radiation dose limit on individual as well as collective dose. So many experts are required for doing the jobs. You cannot assign a skill job to one single person because his dose may get off. So whenever many critical equipment maintenance and is being done and all, so you may have to require many experts in this field. So contractor also, there are limited on the quarterly dose and all. So while you are planning maintenance and annual shutdowns and all, this also comes into critical condition while planning the jobs. Maintaining control area, then high cost of life extension. So already we have spoken. Disposal of radiation waste. This is also a challenge. There one more important thing and most critical for is nuclear power plant in-service inspection. This also takes lot of finance, lot of indigenization and lot of time also in nuclear power plant. As the power plant goes older and older, the amount of in-service inspections increases, and there were earlier plants, old age plants, where at that time the concept was not that all the weld inspection has to be done in the life cycle and all. Inspecting such welds which are inaccessible, we call them that welds are inaccessible. But to inspect that welds, generating, doing R&D and all, formatting, finding tools and all for such type of inspection, it takes a lot of time. So many of the nuclear plants are aging, so ISI, carrying out in-service inspections, is also a big challenge. Then there are component degradation because of corrosion and fatigue. So in-service inspection is a high cost because many of the equipments and all you have to replace and upgrade. And need of modernization also is there based on the need. One more thing which is challenging for a nuclear power plant is workforce and skill retention. Highly specialized workforce is required in operating for nuclear plant. Like just to example, for control room operation for the latest nuclear power plant, you will require 3 control engineers who are having 3 years of experience of operating a nuclear power plant. There are type of licensing which was senior license, junior license and all. You have to take junior license after 2 years of training and spending in the field. It is called junior license, after which you become control engineer. And then after 5 years of licensing and retraining, you become a assistant shift engineer in NPP mode. And then after further 2 years, you become shift engineer. So every control room has to be accessed by 1 shift engineer, 2 assistant shift engineers, and 3 control engineers. And they have to be well trained, and you have to take care of the retraining also, qualification, because every crew and all, they have to go through simulator training, continuous processes that they have to be retrained, and you have to keep their skill in the best condition. So these are the capital and operating costs. High construction cost is there, long project timeline, maintenance and safety upgrade, competition with the renewable energy, and security threats and measures also increases the cost. Public perception, social acceptance, impact of Chernobyl and Fukushima has also dented the confidence in nuclear public. And the safety upgrades has also cost, given, we have to spend a tremendous amount of money and manpower in doing the safety upgrades. Fear of radiation is still there in public. We have to do many CSR activities, many public outreach to remove the fear from the, and this is a continuous process which cannot be stopped. And that also requires money, planning and manpower. Political and environmental oppositions are there. Need for transparency and public trust is essential. We have to be prepared for natural disaster, human error risk, for severe accident management and emergency response. Fuel supply and geological political situation, they are also issues. We have to, for enriched uranium, you have to supply, depend upon the uranium supply chain. Enriched fuel requirement, international political factors may also influence, and long-term fuel security planning, that is also essential part of NPP. We just want to, so you require a technological advancement like small modular reactor, BSMRs, generation 4 reactors, passive safety system, digital monitoring and AI-based diagnostic systems. We have to improve the safety culture of nuclear power plant by continuous operator training, learning from past accidents, international cooperation, and operator experience sharing. My conclusion is safety is the topmost for an operational power plant. Nuclear power plant face technical, economic, and social challenges. Strong and regulation plus innovation will give sustainable future. Nuclear power remains key for low carbon energy. Thank you.
Thank you, Sanjay. We can take a few questions.
Yeah.
From the operational point of view, like as per the Shanti bill, the Spain fuel will be given to the government. So the payment or I'll repeat again. This is Dipankar from Hortic Asia. My question is for the operations point of view. Like as per the Shanti bill, the Spain fuel will be given to the government back. What for the financial security if something happens to the nuclear power plant?
Like even if you, the thing is you have to give the fuel to the government, but like I brought in my transportation is the financial aspect. Even the fuel which have come from the reactor, they have to be cooled for at least minimum 10 years.
Okay.
They have to be cooled in a spent fuel for 10 years. Then only they can be transported to some other place. So when you are designing a nuclear power plant or taking care of, even if you are thinking about, it will come that you have to share it, give it to the government and all. This all aspect will be coming into cost calculation where you have to maintain the fuel pool, store the fuel for 10 years, maintain its integrity. Then there are systems for maintaining its, like reactor pressure vessel, you have to maintain in very good condition, like the chemistry and all. So even fuel pool also, you have to maintain the reactor water chemistry in a very good condition. So this will be challenges and have to be incorporated in the financial aspect of nuclear power plants.
Okay. Thank you, sir.
Sir, Sriram from Connectrix had a quick question for you, sir. You spoke about VANO and VANO peer audits. Just out of curiosity, how are the different fleets doing in terms of, VANO peer audits, and what are the typical areas for improvement that the peer audits have revealed? Is one question. The other question is about tritium. You also talked about ALARA and dose measurements, etc. I don't know whether India has a tritium removal facility. So how is tritium abatement or tritium, the dose associated with tritium managed in the Indian nuclear power plants?
First of all, your question about VANO. So VANO has a functional area and cross-functional areas in which the peer reviews are done. Basically, it is one area is management review, then other area is operation, then technical service review, then it is radiation protection, industrial safety. So normally, because it is the review is done for a organizational benefit, till now, the documents which are given by VANO, it is given to the plant head only. So they are not available in a public domain, what the plant has to be improved. So like USA and USNRC and all, they give whatever the recommendations are there, they are available in the public domain. But VANO, because it is an organization for friendships and all, means at present till they are not disclosing whatever the recommendations they give in the public domain. It is given to the plant management and the CEO of head office, means the same day and all. And now they have started doing benchmarking also, some points they give, but that also is revealed only to organizations and all. So these are, and there are then cross-functions areas also, there are many areas in which the VANO will check your performance.
And what about tritium abatement?
Tritium. No, tritium cannot, means by good measures you can only, tritium can give you internal dose contamination more. So by having a good control, good breathing equipment, suits and all, it can be controlled. You have to have a very good measures and contamination control, then your tritium will automatically get controlled.
If no more questions, then let us give a big clap to Mr. Sanjay for wonderful presentation.
Thank you, thank you.
Thank you so much, Sanjay.